Welcome to another MoTeC webinar. My name's Pete Swinney and today's subject is tuning idle control on an M130 GP Lite ECU. Now we've done idle control webinars before, so this will be quite similar to others. A little bit, one of the few differences with the GP Lite package of course is that we don't have drive-by-wire on it. So as far as the air mass side goes, we have a solenoid or a duty cycle controlled solenoid or a stepper motor. Other than that, the setup parameters are almost identical to GPA and GPR packages. So just a few basics about how the idle control system works. So effectively the primary control uses ignition timing to speed up and slow down the engine as appropriate. As tuners, you'll know that when we add ignition timing from a retarded position, when we add timing, the engine will speed up, we'll make more torque, and then if we wanted the engine to slow down, we can retard the timing to do that. So primarily, the ECU uses that strategy to instantaneously fix the idle error, the aim error, and then it tops up any error that's left using the air mass side. Now some of you won't have air mass devices, so what that means is won't have a stepper motor or a solenoid air bypass valve. A lot of engines simply have a set throttle, aftermarket throttle body without any sort of air idle control system on it. So you can still do a really good job using just the ignition side, and that's the first thing we'll cover off today. One thing I wanted to point out before we go to the next slide is that there's a lot of help on idle control just by pressing our friendly key F1. And so just going on each parameter and either looking to the right of the parameter or pressing F1 will show you lots and lots of help about what that parameter means and the process of actually tuning idle control. All right. So the workflow is basically go through and set up your the main idle parameters, starting with the idle aim, and then if you don't know the right numbers to put in there and you press F1, for most parameters there is some suggested help. So unless you really know exactly what numbers you want to put in there for the proportional and integral and various places, just put the suggested help values in there, and that'll be a good way to get started. All right, and so initially we'll set up the ignition control side of things, which is what you do even if you have a mass airflow device on it. After the ignition side is set up, then we can tune the mass airflow part. All right, now I've got an example of how the ignition side works here. In fact, it also shows the duty cycle of our air bypass solenoid working. So I just want to take you through that. So here you'll see we have, oh sorry, I can't click on that like it's live. If you have a look over here, we had an idle aim of, I think it was 1600, and you'll see that aim has come down to 1300. All right, and you'll see that the engine speed itself followed very nicely, and it's smack on aim. Now if we have a look what the ignition timing did, you'll see the ignition timing is sitting right around 10 degrees, and when it sees the request for a slower aim or a slower idle, the timing goes below, goes negative, goes to our minimum number, in this case was -5 degrees, and that causes the engine speed to slow down quite quickly. Now I just did this actually for the presentation, and it's actually faster than that normally. But we're on an engine dyno with quite a lot of mass, so it's quite slow in slowing down because you've got all the dyno, water head and so forth bolted to the engine as well. So a little bit like a transmission I suppose, but worse. So anyway, you'll see the timing goes to negative to pull the engine down, and then once the engine gets to its aim idle, the ignition timing comes up again to what we call the target timing. Now the reason that the timing is able to come up is because in this particular case it's got the idle solenoid working as well, and if we go back here, when we were at our higher engine speed of 1600, you'll see we were running 50% duty. We requested the lower idle aim speed, and our duty cycle came straight down. It looks at a feed forward table for the duty cycle, so immediately comes down to that duty cycle number. The timing pulls back to try and help that happen quicker, and once the engine speed slows down, then the timing is able to ramp its way back up to a central location halfway between maximum power timing and minimum power timing. And so the idle is now running at a lower engine speed based on the fact that the duty cycle has slowed down, or is a lower number. It's gone from 50 now down to 24. And so the duty cycle kind of chases the engine speed along to keep it on its aim, and the timing is the part that responds quickly if it needs to change. So when they request for the idle to go higher here, you see the green line goes up to a higher number. At that moment that happens, the ignition snaps up to the maximum allowable ignition, and let's see that. Yeah, the maximum allowable ignition, which speeds the engine up. And then once the engine gets to its aim, of course, the timing can come back again, and the duty cycle is at that higher, or at an appropriate number to maintain that higher aim RPM. All right. So that's an overview of what happens. So again, we just set all our idle control parameters up to their defaults, and then before we get started, we need to make sure that our main ignition table, so this is the main ignition table here, has the correct numbers in it to make maximum best torque at idle. So in this case, for this webinar, we're going to have idle numbers between 1200 and 1500, just because that's where this engine likes to idle. And so what you want to do, the first thing to do is to make sure that you've got MBT numbers in your ignition main table, so that when we need to make power to speed the engine up, we've got a good amount of ignition timing in to do that. So for most engines, that's 14-15 degrees for a kind of a modern Japanese engine. For like an older style Chev, that kind of deal, you might be getting up to numbers of about 24 or 25 to make maximum power at idle. I know that sounds a little silly, but that's what you're after. So get that curve right, so that the idle control system, when it needs to make the engine speed go up, it actually refers to the number in this table to do that. All right, I keep repeating about the idle control parameters being all set to their defaults. That lets you know how important that is. So one of the key parameters to tune is the ignition timing limit advanced target. So what that means is this is where you want the ignition timing to be when the engine is idling correctly. All right, so it needs to be halfway between the power that it would make with the main ignition timing, MBT power, and between the minimum parameter that you're going to set, which is the ignition minimum. So obviously the more retarded the timing, the less power the engine will make, but there is a limit as far as that goes, because if we have quite a lot of butterfly open and a very retarded ignition timing, we can create quite a lot of exhaust temperatures, or high exhaust temperatures. So we don't want our minimum ignition timing number to be too low, otherwise we get too hot exhaust temp. And so somewhere between -5 and -10 degrees for a Japanese engine, late model sort of engine, and standard condition. But the likes of an LS engine doesn't like timing much below sort of 2 or 3 degrees. Either way, you've got to run a timing number, minimum timing number, that allows the system to be able to reduce power, and that's just offset, as I say, with the fact that you may have too much exhaust temp if you go too retarded. Most OEs are using around -5, -6 degrees as their minimum timing, is my understanding. All right, then you're setting your proportional gain for your ignition side control. Again, just look at the help and put in the numbers. Somewhere between 150 and 250 is pretty good to start with. And there's no integral gain actually on the, that's a mistake on our sheet, there's no integral gain in the GP Lite package, because most of the time the idea is to set that to 0, so we've done that in the background. All right, on the mass flow side of it, you will have three choices. You'll either have no airflow device, no stepper motor or idle solenoid, or you'll have you'll either have no control, as in no device on it at all, or you'll have a stepper motor, or you'll have an idle or a duty control idle solenoid. So if you do have an idle air bypass motor of some description, then the process there is to give it some feed forward numbers to start with, and that table that we use there is called the idle mass flow feed forward main, and effectively that is either duty cycle directly to a duty control motor, or it's a percentage of steps that we define for a stepper motor. So if a stepper motor has 200 steps, then we put a number of 50 in this table. That basically means 100 steps. All right, so you fill out this feed forward table. We'll go. It's much easier for me to show you live how to do that, and depends on each particular aim that you have requested and the temperature of the engine as to what number you put in this table. All right, so that's it on that side. It's much better to do this live. So let's flick over to the engine and let's go through it here. So this is the GP Lite worksheets for the idle control, and you'll see quite a few parameters not here compared to GPA. A lot of stuff we've put preset in the background to make life easier for you guys to set this up. So effectively we're going to turn the idle mode onto enabled. This parameter here means the throttle's got to be, or the throttle position's got to be 2% or less before the idle control steps in. The idle timing target, so this is our ignition timing that we'd like to target if we're using an idle air bypass, a motor of some description, stepper or a duty cycle control. So the timing makes the instantaneous change, and then the air mass side moves its control to allow more and less air to allow the timing to come back to this target number. I know this is awfully confusing if you haven't understood this before. So that's the middle point. This is the minimum number that we're going to use for our ignition retard, if you like. So the ignition control side uses this as its minimum if it wants to slow the engine down quickly, and it uses the ignition timing main number as its maximum and uses this as its center point. All right, there's our proportional gain. I mean, let's enter the actual number from the help. If we just go back up to any one of these parameters, I'll just press F6, and you can see, if you look at this, study this diagram, it gives you an idea of how this ignition side works, how it adds timing to increase power and subtracts timing to decrease power or torque. Okay, F6 back again. All right, so right now this has got a duty cycle motor on it, but I've turned that off and set everything to 0, so it has no effect. So I just want to show you what happens on this engine when we're just using the ignition timing, and how it responds, and what happens if we change a few parameters. So, all right, here we go. So here's our idle aim, and in this case we're going for 1000 RPM. Right, and we can see at this particular engine speed that the ignition timing to hold to 1000 RPM is, it's varying somewhere between 2 and 3. Depends on what loads on it and so forth, and how the engine's running as to how much timing it uses, and either in retarded or advanced to get the engine to where it needs to be. So if I lift the aim up, sorry, I'll just go back. Because there's no air control side, the ignition timing has to stay wherever it's at to maintain the idle. So there's no ability to come back to its timing target, because there's nothing on the air control side to allow the ignition timing to come back to the middle. But if I aim for 1200 RPM here, all right, you'll see that now the engine speed is come up to 1200, and our ignition timing, you see it popped up there to get the engine to lift quickly. And if we go to 1400, all right. Now the fact is we can't quite reach 1400 because we're running the maximum timing we can to get there, and more ignition timing won't actually lift the engine speed anymore. So that's the range of engine speed that we can move with just ignition control only. Now if you want that to be higher, you would open the butterfly, and that would allow the engine speed to come up. If you want it to be lower, then you would close the butterfly. And so the idea is to open and close the butterfly till you put the ignition timing in its middle position. So if you want this engine speed to go above and below 1400 revs, then you would open the butterfly and keep opening the butterfly. Engine would speed up, and then as you kept opening the butterfly, the timing would keep coming back, and you would keep opening the butterfly until the ignition timing got to your 9 degrees. And what that would mean is, with a base of 1400, you could then request, say, 1600 or 1200, and the engine speed would go to those two values. All right, so currently, based on where the butterfly is, we can run somewhere between 1360, 1370 and around 1000. So sort of around 300 or 400 control range using just ignition timing only. So if we come back down to 1000 here, all right, you'll see the ignition timing comes right back down. Now the reason it's sitting slightly above the aim, that's because we've got our proportional isn't pushing it harder. So if you really wanted to force it down, we could run the 300 or even 500. It just makes the control unstable. You see it's pushed the engine speed down a bit. I'll just show you what happens if we get really crazy. All right, and see what happens if we have too much proportional. We're right on our aim now. It's jamming, but it's bouncing up and down from one end of the control to the other. All right, but we have met the aim, but it's not very nice. So we go back to 300. All right. So ideally, if we want really a nice big wide range of idle control, we need an air control device. So if we want to be able to move our idle speed from, say, 1000 to 1600, then we need something else to increase the power of the engine. And the best way to increase the power or the torque of the engine is to add some more air. So if we pop over to our air control side, you'll see now we have some more parameters to fill out. So we've got an idle mass flow feed forward main, which currently has 0 in it. So if I put some numbers in here, and let's something like 30. All right, so now we can see on our duty cycle we have a number of 30, but the parameter or the PID parameter that we use to control our air side is integral. All right, so we have an integral gain here. As per the help, it's 160, but our integral clamps here I put them to 0. So in order for the air side to be able to have some control, we need to allow the integral to move to fine tune it. So if our feed forward number is not correct, then we need to allow the control side of it to be able to do that. Now you can see that our integral is wound all the way down. See, here's our live integral value, which is -20. All right, and that's because our duty cycle number is too high here. All right, so we're down to a number of 10. We're actually aiming for an RPM that is, the butterflies are almost closed. So the engine speed we're aiming for here is a little low for the demonstration. So if I go to an aim of 1300, and this is the way to tune the idle mass flow feed forward main table. Go to our aim. All right, so here we can see we have our aim of 1300. It's being met. The integral is now pushing the duty cycle of the solenoid to the number that's required to meet the aim, because once the engine speed reaches the aim, the ignition timing starts to come back to its target. So it's looking to come back to its target. All right, so now it's kind of halfway between its -5 and 15 that we've got in the ignition timing main table, and you can see the correct number for the feed forward table here is 20. All right, so that has been calculated based on the feed forward number of 30, and you can see the integral is pulled out 9.5. So if we just, for this engine temperature, type 20. All right, now the solenoid went right down here. And the reason it went right down is because the integral was pulling out 10. So the integral, you see, starting to wind back to 0 or close to it. And we know we've got this feed forward table pretty close to right when our integral correction is around 0. We want the integral to be around 0 or 1 or 2 for each setting. All right. So when the engine's cold, for an aim of 1300, at each of these coolant temperatures, you would come in here and adjust this so that this integral correction was somewhere around 0, 1, 2, 3, 4, something like that. All right, so you see the idle is around the target now, and if we go for a quick change here, then that will respond quickly. But let's just tune our 1500 sight for our feed forward. All right, so now our feed forward's here. So this number, it's using 30. Let's see what number it needs. So the integral's winding up now to correct it. All right, so our timing is back down on its target, and it's using about a number of 40% duty to achieve what it needs. I'll put the correct number in, and now you'll see the integral correction coming back out again. All right, and you can see the engine speed smack on the aim. Okay. All right, so anywhere between 0 and 5, -2, doesn't really matter. This all changes depending on what's on the engine, whether it's in gear, out of gear, that kind of thing. All right. The integral will fix any minor error. The ignition timing fixes an instant error, and then the air control side comes back and fixes it over a longer period of time. Let's tune the last sight, which is 1800. All right, so we know this number of 30 is going to be wrong. Let's type 45 to start with. We can see it's actually even higher than that. You don't actually want this number to be too high, because if you're coming back into idle control, if this number's too high, then it will cause the idle control to not go into idle control. So to be honest, you really don't want to tune this number perfectly. It actually needs to be a bit lower to help it come back down into idle control. All right, but you can see it works perfectly, it's sitting smack on 1800. It's right on the target, so if you did want to get this exactly right, all right, the number would be 68. You can see that there with our integrals putting in 3, so it's pretty good. But The only reason you'd ever want to be at 1800, there is a feature that adds, when you go out of idle control, it adds an extra 500 RPM to the target idle to allow the engine speed to come down to that higher number, and then it ramps down slowly to prevent stalling. So we really don't want that number to be as high as what you think. I know that doesn't make sense, but it'll work. It'll work better if it's like that. Alright, so we'll end up tuning these numbers to be a little higher when the engine is cold, because the oil is thicker at that time. Alright, but even there, that's quickly done, and it'll work quite well with the ignition timing helping the instant errors, and the integral component fixing anything else. Alright, so we'll come back down to our intended idle. Alright, so you see the behavior again. As soon as we request the lower idle, the timing goes down to our minimum, pulls the engine speed down. As soon as the engine speed's on aim, timing goes back to its central location. Let's just unpause that for a sec and pause it again. Alright, and the timing's not quite at the 9 degrees, but the duty cycle, the integral's winding the duty cycle in, basically, so the timing can come back up again. Alright? Simple as that. Okay, so hopefully that's a reasonable explanation. I know it's a lot to take in. Have a practice and read the help, and it'll go well. Thanks for listening. Catch you next time.